Hello everyone, I'm Max and welcome to our 7th lesson series. Last time we covered sequences and now it's time to update our knowledge on how we apply them. You may hear I have a better microphone, which is what I'm gonna be using from now on to make content. Hopefully this is a lot better. If you guys don't like the sound, feel free to comment under the video on how I can improve it, because I do try to make everything I can so you guys can have the prime experience of learning. So there's least distractions and the quality of my content is good enough for you to actually understand what I'm teaching. First, let's clarify the difference between the previous lesson and this one. Sequences are essentially lists with elements that are in some way connected and in some predictable order, where nth term being on nth place, etc. While series is or are a sum of all the elements or terms of that list, or in some cases a few of the elements if that is what we want to calculate, or if the sum of all elements would be impossible to determine, as the value would keep changing and would not approach any fixed value with each further addition. But don't worry about anything. In this video we will see how to know when we can and when we can't add infinite terms, along with how this property is called. Now let's take an example of the finite sequence that has 4 elements or terms, which are the first 4 even numbers. So that's 2, 4, 6, and 8. The series of it would be the sum of these numbers, so 2 plus 4 plus 6 plus 8, which is equal to 20. Now, so the mathematical symbol for the sum or addition of elements is an uppercase Greek letter S called sigma. And it looks like this. This is the uppercase one, which we use for the sum, and the second one is a lowercase, which we will run into more in physics and definitely in chemistry. There's also a symbol for multiplication equivalent to a series. I don't think there's a word for that, but that is not important for this video at all. But the symbol basically tells us that we take all the terms and multiply them together instead of just adding them like we do in series. The symbol is an uppercase Greek letter pi, but again, we will get to that when we need it, maybe in a YouTube short as a fun fact if nothing else. So for now, let's focus on the sigma notation, how we can use it, what it tells us in more detail, and then we'll see how it applies to what we do, although I don't think I'm gonna be using it in this video because we just find a formula, but it is important to point it out because I may be using it to simplify some writings. Now first, we use it to write sums compactly, basically to highlight the structure and to make it easier to plug into other formulas. So let's say that I have a series, long series, infinite series, which has infinite terms. And I can't just plug that into an equation because that would make it an infinite equation and hard to predict. So I use the sigma notation, which would basically look, I'll show it on the next slides, but basically just compact that series into one short form, and then we just work with it. But again, we'll cover that later. There's also another notation that we will learn sometime after functions, and it's called an integral. It also applies to additions or sums, but in some different way. It may sound complex, but I'll make sure to explain it in a way that even a toddler would understand when it comes to it. There are 2 ways to use a sigma notation. Use whichever one you prefer. The second one is more common and slightly easier to read, but the first one is the default one that the PowerPoint uses when you try to format it as a sigma. This one took like 3 text boxes, so I could align it all perfectly. Now, what each part means. The AI, so the ith term, is the term in the ith place. So we said nth term before, but sigma notation we call it I. You could replace it with an n to be easier to follow along, but you may be confused with what the n above the sigma sign is and what this one instead of an I would be. So this n, to clarify what it is, means the last term of the sequence that you are using. So if you want to add the first 5 terms of a sequence, n above the sigma sign would be 5. If you want to add 200, n is 200. All the way to infinity if you so want. Now, under the sigma symbol, you clarify which letter is changing. So if you use AI as the term, so ith term, then I is meant to be changing. So you start with this I equals to n1, which is the first number, and this is the last number, so you just replace the term in here like so. A1, A2, A3, all the way to AN. I think that's essentially sums it up, but I'll jump onto an explanation on an example so you don't have to worry about it. And with all that together, it means that we add all the terms from the one where I equals n, n1, and until the last one where I equals n. Since this may be confusing because I do not know how to explain something cohesively, let's go step by step on an actual example. So I have a sequence, or right now writing for a series, where we have first 4 terms we want to add together. The formula for the sequence or the further terms is 2 times n, and n equals 1. So as you see, I used n instead of I. So the first term we use is where n is 1, which is 2. So 2 times 1 is 2. This entire formula basically means that we are going to be adding together all terms from n and 1 to n ending or whatever. So let's break it apart. We specify which n it is, so first n, second n, third n, and fourth n. And now we just plug in the numbers. Since n's change by 1, so 1, 2, 3, 4, we put them in, and 1 would be 1, and 2 would be 2, and 3 would be 3, and 4 would be 4. So we have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, which is 2 plus 4 plus 6 plus 8, which is 20. So we see that what is written in this part of the first line, the sigma notation, is a shorter version of writing all of that, or all of that, or all of that, whichever line you prefer to see. And in many cases, there are more terms, so this notation is preferred a lot more than this long one. Now let's learn how to solve these series with a simpler equation or a formula, so you don't have to manually or in your brain do this math. So let's see how we get it. Let's start with an arithmetic series, which is a sum of the terms in arithmetic sequence. It is important to know that we cannot have infinite arithmetic series, as they do not converge around a certain sum or result. I'll probably say this a few times, but that's just because it is important to know, so you can see that the meme of sum of all natural numbers being minus 1/12, is firstly impossible. Secondly, if it were possible, it would be because it's a part of a bit more complex part of math, and wouldn't represent the actual sum of natural numbers. It would just be basically like multiplying both sides with 0, saying 0 equals 0, so 1 is 2, you know. Now, let's get back to the topic. Let's first write a standard formula for a sum of the first few terms. I'll mark the sum with S, as I'm not using the sigma formula. I'll use just S, so the English letter, or whatever the alphabet is called, I forgot. Now, if you remember, the difference added to get the nth term is n minus 1. So as we're adding to the first term is a, the second term is a plus d, third term is a plus 2d. The difference multiplied with 1 less than the n value of the term is the further term, so the last one, meaning that the last term would be the first one plus the n minus 1. So I hope you still remember the sequence formula, so we don't have to cover that in that as well, because my language is completely gone apparently. Next, we have to add the series in the backwards order. So we rewrite it in the other way around. So the nth term is first, plus previous one, plus third, plus second, plus first. So we would add the nth term to the first one, second term to the n minus first, and the last one to the first one. So technically the sum of n positions would be 1 more than n of the last term. So if we sum 10th term, the sum of both terms' positions must be 11. So you added the 10th term to the first one, you sum the positions. So 10 plus 1, 10th term plus first term, that's 11. That way, every single pair, so the first and the nth term and the second and the pre-last term, their n always sums up to n plus 1. Or basically, it's always the sum of the first one in the sequence and the last one in the sequence that we added together, like we folded a piece of paper, touching both ends together, so the half point where it bends just means that the third, if it's 3 centimeters away from the half, on either side, it's gonna be touching together after we fold the paper. But why do we do this? We have to see that if we add them in such a way, we would be able to add a's together in both terms, getting 2a plus n minus 1d in all. If you don't believe me, you can try it for yourself too by writing for any two terms like n minus 2 and n minus 3 and so on and so on. But for now, you just have to take my word for it. Now, since we added them together and got the same term from all pairs, when we added n terms in both series, we will get n of the same terms. So let's write it as such. So basically, a plus n minus 1d would give us 2a plus n minus 1d. And if we repeated it for the same process, so let's do the first and the last term and the last and the first term, you see that we get the same sum. And now, since there are n terms of all that, we would just have to multiply that by n because we had a series of n terms. So that's what this n is. But since we added two series together, so we just like with equations, if you remember a couple of lessons ago, when we add two equations together, we add left side to the left side, so this s plus this s, and we add the right side to the right side. So we get 2s is n times 2a plus n minus 1 times d. Now, to get the actual sum, or the series value, we divide both sides by 2, and we get our final formula, 1/2 times n times 2a plus n minus 1d. This square bracket is used because n is multiplied over this entire two-term expression. Now that's one way to get it. The other one is basically the same, but slightly different and easier because it's a bit more simple to visualize. Now for this one, the second way to get it, it's basically more intuitive. First, we know that if we add any two numbers together, like a and b, their sum is equal to the sum of their average. So if we take the average of a and b and add it to the average of a and b, the two would cancel it out. So we would get 2 times a plus b halves. And that just leaves us with a plus b. Next thing we need to know, or at least see, that if all terms are equally apart, the first and last term have the same average as one term before and the second one. Let's take even numbers up to 10. We see that the average is the same. I use this notation for an average because it's easier than writing fractions, plus in Microsoft Excel, if you use this notation, I think this gives you the average. I may be wrong. But yes, it's one of the ways I can write averages on PowerPoints because it's just simpler to read. But yeah, if we see that we take the first and the nth term and the second one and one before nth, we see that the average between the first, in the first example, is 12 divided by 2 is 6. In the second, it's 12 divided by 2 is 6. And now, because we have one term left, we just use the average of one term, so 6 divided by 1, which is 6. We have 3 averages that are the same. So with that logic, we can see that we can reduce a sequence or series into less elements that are easier to add up. So we already have a part of the formula where we add a, or the first term, and a plus n minus 1d as the nth term, so the last one, divided by 2 to get their average. Next up, we need to account for all the averages. Now, if we remember the sum rule, we added 2 terms, so we have to divide by 2 to get their average, or we multiply the average by 2 to get the sum of the original 2 numbers. Here, we technically did get the average from 2 terms, but we got it n halves times, sort of. We could have put all the numbers and get the average of all of them, so 2 plus 4 plus 6 plus 8 plus 10 divided by 5, and we would still get the same result. You can check it out if you're interested on how and why, but that's technically part of statistics that we will not cover just yet. Maybe, I do not know when we have statistics, honestly. But yes, when we get to statistics, I'll definitely mention this and I'll return to it. And it's a very helpful tool as well. I mention examples later on, I see. But yeah, since we got the terms, since we have the average of since we have the average of 2 terms, so the first one and the last one, which is equal to the average of all terms together, since this is an arithmetic series, we can multiply it with the number of terms, so n, which gives us the sum of all terms. That number needs to be multiplied with the average, can also be the sum of the numbers in the denominators of individual average calculation brackets, which I have colored orange here. That sum is 5, 2 plus 2 plus 1, and that is also the n, so the number of terms, or the amount. So the amount of terms we're adding together. And now for the example that I foreshadowed. This is super handy for calculating averages for like grades, since if you want to have a certain average at the end of the year, you multiply that wish number or the desired average with the number of grades that you can get altogether in that year, then subtract the current sum of the grades that you already have. And if you have letters like A, B, C, whatever, just assign them numbers or even go by percentages. Percentages might even be the best way to do it. Now that you have subtracted it, the number you're left with is the sum of all the grades you need to get to have the desired average. So if you're missing 8 exams and you have a sum of 80, you would need to get 10 on each of the exams to have the desired sum. The desired average at the end of the year. And if you divide that number, as I said, with the number of grades, so 80 and with 8 grades, you can see the exact grades or the average of the grades from the further tests you need. So the test you haven't taken yet. And that average is basically like on a smaller sample. So instead of calculating the average of 12 exams, you know how much you need to have on the next 4 exams. So let's say I need to have an average of 7.8 on the next 4 exams. So I don't have to calculate with all the previous grades. I just have to account for the fourth one here. So if I have a 7, a 7, and a 9, and a 9, that's the average of 8. So it's obviously above the average that I wanted. So I'm going to have a better average at the end. Basically, a lot of math behind this. I hope I got the point across. Yeah, from personal experience, if you're trying to improve your average, the one from not taken tests will be a lot higher. So that obviously makes sense, because if you're comparing two sets of numbers and want the average to be some value higher than the first one, you have to have a lot more. But then again, depends on how many exams you've already had and so on. If you want some homework, I can give you a hint. The average between the tests you have not taken yet and the tests you have, like how much higher does the second or the higher average have to be for you to still have the desired average, is based on the ratio of how many tests you have in each of these groups. Now for the homework, you can calculate the formula for how much higher or lower than the desired one must your new average be based on the ratio between missing and taken tests. So let's say have a sample of 10 tests. You took 5, you still have to take 5. You have some average from the first 5, and you want to have like 1 grade higher average altogether. You can, for the homework if you want, or if you want to master this topic, solve it for yourself, how to get that formula, how to calculate exactly. But of course, this is not mandatory, this is just for you if you want to know a bit more. Anyway, I did get sidetracked. Also, this is very advanced, so you don't have to do it. It's just a good brain workout, and I can recommend it. But yes, I got sidetracked. As I said, and as we saw, we need to multiply the average that we got from the first and the nth term with the number of terms to get the sum of the entire series. So we got the equation we got before. Basically, just replace the nth term formula with this part, and you get the same thing. Now, for our first example, let's try to use the formulas, see if we learn them. We see that the difference between each term is 5, and the first term given is also 5, and the number of terms is 4. So we have difference, first term, and n. So n, which is 4. Now let's get the equation and paste in the values. So 1/2 times n times the bracket of 2 times first term plus bracket of 1 less than n times difference is basically 2 times 25, which is 50. This is using the longer formula. Next example will be using a shorter one, where you use the first and the last term. So we have 20 plus 17 plus 14 plus 11, first term, last term, and the amount of terms. We have half of n, so half of the amount of terms, times the sum of the first and the last one. We have 2 times 20 plus 11, which is 2 times 31, which is 62. Now we have seen how to use both formulas, so let's solve the last example before we move on to the geometric series, because it's already been, holy god, I've been recording for a while. Example number 3, 1 plus 4 plus 7 plus 10 plus 13. First term is 1, nth term is 13, the amount of terms is 5. So we use the short formula, we plug in the numbers, we solve the bracket, we multiply, so we have 14 divided by 2 is 7, so 7 times 5 is 35. Hopefully, we've learned how to get the formulas, when do we use them, and we actually remember the formulas, or if we don't, then we know how to get them if we need to. Now let's move on to the geometric series. So we know each term in a geometric sequence is basically the previous one multiplied by the ratio. So let's write it out as a series, just like we did with arithmetic. So the first term, the second term, the third term, and the nth term. Now we have to multiply the equation with r, so the ratio. What the hell am I doing here? Oh yeah, this is the original one, this is the one multiplied with r. Now we have to subtract s on the left, and on the right we subtract the value of s. So here, like we did with the equations, so let's say this is some variable like x. We have x on the left side, so we subtract as x, and on the right side we have the value of x, like y plus 3z. But yes, we subtract that, so we have, as we had written before, we have a plus ar squared, all the way to the ar to the power of n minus 1. This will cancel out all the terms between a, right here, and the arn, because this one, diagonally they repeat, except for the last one and the first one. So if we take the difference, we will only be left with the last nth term and the first term, but since we took it away, it's minus first term. Now we can multiply or divide both sides with minus 1, so we have the first term as the positive one, and at the start of the equation. Now let's try to isolate s, so we can get a simple formula, so let's factor out the s on the left and a on the right, and we see that we just divide the entire equation with 1 minus r, so we have two possible, oops, I forgot to edit this one, I fixed it. As we see, we have two formulas, one where we have it as we got it before, and the other one where we multiply it again with minus 1, or because as we all know, if a fraction has a negative sign in front of it on both sides, so above and under the line, it's the same value, so it's like multiplying -1 with -1, it gives us 1. So, but yeah, these are the, oops, I lost my pen. These are the two formulas, which are basically the same, but this one is gonna be negative on each side of the line more often, but so whichever one is easier for you to remember or understand, that's the one you can use. They're basically the same. But it's important to know that these two formulas are only for finite geometric series, as we see the n for the number of terms. Oh, what the hell? And we will get to the infinite series in a bit, so let's try to practice the finite first. First example, we have 4 terms. First one being 2, the ratio being 2. Amen. Okay, just ignore this. I have apparently misspelled this a lot. So we paste in the numbers. This is correct now. So we have 2 to the power of 4, which is 16, which I write it out like this. So 2 times top part of the fraction, which is 1 minus 16, divided by minus 1, which is 2 times minus 15 divided by minus 1, which is 2 times 15, which is 30. So the sum of these 4 terms is 30. Now, example number 2 of the geometric series. We have 3 terms, first one being 81, the ratio being 1/3, and n being 3. Again, the formula is bullying me, because superscript on PowerPoint, when you copy, just doesn't stay on equations. But when I insert the numbers, I make sure that it's correct. So it's 81 times 1 minus 1/3 to the power of 3, divided by 1 minus 1/3. So we solve that out. 1/3 to the 3 is 1/27. So we have a lot of fractions. So let's just try to solve inside brackets first. So we have 81 times 26 divided by 27, because this can be written as 27 divided by 27. So if we take 1 away, it's 26. Now, since we're dividing, we use the zigzag rule, or whatever it's called, where we give the top part of the bottom fraction to the bottom of the top one, and the bottom of the bottom fraction to the top of the top one. Just basically, as I saw the arrows, That's how we multiply them. So 3 times 26 and 2 times 27. Now we can cancel them out because 2 is multiplied with 27. We can cancel out 2 here and 2 from 26, so we're left with 13. And we can cancel out 3 and 27, so we're left with 1 and 9, so it's 13 divided by 9. And now since we're multiplying this fraction with 81, we can cancel out 9 as well. So 9 times 9 is 81, so we're left with 9 times 13, which is 117. This one was a bit more lengthy to solve, but nothing too hard for you guys. You are very smart. I believe in you guys that you can understand this. Now, geometric series example number 3. It's a sum of the first 4 terms, but we see that it's also alternating. And as we know that alternating sequences can also be geometric. Here, it's an alternating geometric series. Does it really change the way we solve it? Now, let's see. Let's use the formula and check for ourselves. Again, this n should be in a superscript, so exponent to r. So like this. Now we have 5 times whatever this mass on top is and divided by whatever this mass on the bottom is. Let's clear it out a bit. 2 to the power of 4 or minus 2 to the power of 4 is 16 because it's an even exponent and a negative number inside of brackets. We have 1 minus 16 divided by 1 plus 2, altogether multiplied by 5. So minus 15 divided by 3 times 5, and that's minus 25. So we see that the formula works even on alternating sequences that turned into series as long as it's also geometric. Now let's move from finite to infinite. Again, I hope you remember that we cannot have infinite arithmetic series as the numbers diverge. What that means will be shown in just a few slides. As for the sum of natural numbers being minus 1/12, it's derived from methods like zeta functions and other processes. But it's important to know that we are working with infinities, which are not numbers, but they are concepts. So addition, multiplication, division, and everything else, even comparison sometimes, are often impossible. But to get back on point, the methods used to get that number, minus 1/12, are not stable or linear near infinities, which basically means that they may be useful in some range of values. However, outside of that range, they will not be precise enough. We will learn about this stuff more when we get to trigonometry, I think. Oh yes, we do. There is an approximation like how sine of x, where x is some angle, if x is very, very small, the value of the sine function is basically just x itself. So the difference between the actual x value and the value of the sinus x is negligible. But yes, in chemistry, when we will cover calibration curves and standards, etc., we will see what these ranges actually do, like why they are so important, because inside that range, the response from the input may be linear, but right after that range or right before it, it may go exponentially weird, like it can start curving, it can just rise way too fast, flatten out. So it's important to remember that infinite series arithmetic are impossible, and infinite geometric series have a couple of rules. So now let's learn when can we calculate, so what are these rules, and how to calculate if we can. So the first rule is convergence. I already mentioned the diverging and converging. If a series is converging, that means that we can add it together, meaning that the terms, when added together, converge on a single value. If they diverge, they're not approaching that value, and with every addition, the change is big enough that we cannot approximate it to one single result. So the sum of infinite terms is only possible if the terms themselves don't increase too rapidly, meaning that if we add infinite of them, they will be small enough to approach a certain value. Like how we had 1 over x and x approached infinity in the last video, we saw that the terms got closer and closer to 0 but never touched it, meaning that if we added them together, the change would eventually be small enough to not make a difference at all. If the absolute value of the ratio is less than 1, then the series is converging, aka the sum approaching a value that it doesn't exceed regardless of how far in the infinity we go. The opposite of that is divergence, where we can't get the sum. The formula, I'm not going to derive it, but if you're curious, you can try it on your own or just reverse engineer it for this formula. by breaking up the fraction and then just doing the opposite of what we did for the finite geometric series. But yes, this is the formula. It's not important or as important to know how to get it as it is to know when to use it. Also, it's hard to graph out some series because Desmos doesn't like making points graphs. It just likes to connect them. And some graphs will be impossible to be connected because they have no in-between values, even in series. But let's jump into the first example and see that this geometric series has the name. Okay, so let's jump into the first example where we have this geometric series which has the next term 2 times smaller than its previous one. So we have the first term 1, the ratio being 1/2, and this is how the graph would look like if we were to connect the dots from the sequence, of course. The region with the negative x is what we get from graphing. As we all know, the sequences don't have negative ends, not even n equals 0. But yes, we see that the points keep getting closer and closer to 0. So let's see what we can get if we add them together. A is 1 and r is 1/2. So we see that this is between -1 and 1. In other words, its absolute value is less than 1, which means we can use our formula. So we give the formula, we plug in the numbers, we solve under the line, and we get 2. We see that they add up exactly to 2. Now let's see how this formula for finite geometric sequence would solve this, and we can actually do this visually as opposed to some other examples. This is just the finite formula, if you remember, but this x goes towards infinity because I just graphed it as it going to infinity. And the condition of x being greater than or equal to 1 just means that this is like a sequence. We started with the first term, second, third, fourth, fifth, sixth, etc. On the top left, we have the equation, so this is the graph that it corresponds to, as we can see in the color. But yes, this looks horrible now that I look at it. It's a painful number. There's also another property that we can show, like adding together squares or rectangles. So we see how we started with a square on the left, so the surface of it being 1, then added half of its surface, so half of its surface. Then we added half of the last rectangle surface as a square, and we keep repeating that. This is visually how we get the 2 answer. We keep adding the half of the previous term, and we will eventually reach 2. Now, that happens in infinity, but we can approximate it just like in limits. If it's actually filled for 2 entire squares, that's a question for a different topic and for another day. That falls more under limits and statistics, but in context of when it's safe to approximate to avoid making an assumption that could lead to a huge error if using calculations. But yes, it approaches 2, and we will assume it is 2 and somewhere in infinity, as this goes on forever. Example number 2. Now we have another alternating series. Since it's alternating, it's very hard to graph it visibly, as I said before, other than putting every point manually, and Desmos just doesn't like individual points. So the first term being 3 and the ratio being -1/2, as we see it, -1.5 divided by 3 is -1/2. We get the formula, we paste in the values. Now we add 1 plus 1/2, which is 1 whole plus 1/2. So yeah, and we simplify that to 3 halves. 2 goes up, 3 and 3 cancel out, which is 2, and result. Again, unfortunately, I can't graph it because there's just a bunch of points that are never visible. It behaves similar to I wish I could graph it, but you wouldn't understand it because I wish I could graph it, but I wouldn't understand it because we haven't covered that. But there is some equation in physics that behaves pretty much like this, basically converging on a point, going above and under the value itself. But yes, it's cool to see, and I'll definitely try to do it when we get to physics. Example number 3, 2 plus 4 plus 8 plus 16. First term is 2 and the ratio is 2. So the series diverges because the absolute value of the ratio is more than 1. Meaning that this geometric series does not have a sum. Yeah, we see that this infinite geometric series does not have a sum. Now, for the mini-test, this mini-test will contain mostly series, but also need a bit of critical thinking and maybe using some formulas from sequences. Some of that may come in very handy if you have forgotten, so I recommend revisiting the lesson or at least the notes, or just to refresh the memory, if you want to solve the mini-test, of course. Announcement: if you watched so far, I am very thankful. I begin streaming this summer, well, more accurately on Monday. My stream on Monday starts, where's my schedule? Oh yeah, you can follow me on Twitter right under this line, like this laser pointing down. This is my Twitter link, and this is my Twitch link. You can follow me on both of these. On Twitter, I've posted my schedule, and on Twitch, I'll be streaming. I'll be streaming on Monday at 5 p.m. GMT plus 1, so I think that's 5 p.m. London time, or 12 at noon ET time zone. Where this is when I'll be making the Vtuber tier list of which signs their model reminds me of. And the second stream next week is gonna be on 18th of June at the same time, when I will be playing Minecraft or whatever other game I come up with. After that, I will change up my schedule a bit because this week only I had no time on every other day, but I still wanted to start streaming. So yes, I would appreciate you if you drop by when I'm streaming, gave me a follow there, and came and hang out with me. But that's it for today's video. I hope you go and solve the mini test. I hope to see you around. Have a good day and see you on our next quest. Bye.